Good evening. This is Dr. Pradhan here. Welcome to NPTEL project on econometric modeling. So today we will continue the autocorrelation problem. So in the last lecture we have discussed the basic framework of autocorrelation. So let me highlight here what is the basic issue of autocorrelation. So for autocorrelation we have the a function like this, yt equal to alpha plus beta xt, okay, plus ut. So here ut is equal to rho ut minus 1 plus bt, okay. So by the way, if we expand, then ut ultimately will come to it will be summation rho to the power s bt minus s and s equal to 0 to, you can say, n, okay, or you can call it infinitive. When it will equal to infinitive, then obviously the structure of autocorrelation is like this. So now the framework we have already discussed. So right now we will be very specific. What is exact the issue? How you have to detect, what is its impact, and how it's how we are going to solve this particular problem. So that means, so far as autocorrelation is concerned, so we like to highlight here what is the exact problem, what is the problem of autocorrelations, okay. Second is what are the causes, okay, what are the causes of autocorrelations, okay. Third, consequences for detections. Then fifth, removal measures. So altogether 5 components we are going to discuss. So what is the basic framework of autocorrelations? What are the causes, why autocorrelation happens, then what are the consequences, then detection criteria, then the procedural measures, okay. So now autocorrelation basically deals with correlation among the same variables, that too in error terms here. It is a deductive part of regression modeling or econometric modeling. So the moment you see what is the actual procedure of econometric modeling. So you have the mathematical form of the model, then you get the statistical form of the model, then you estimate the model, you have the estimated model. So now true model, estimated model, by the way we will get the error terms. So now the moment you will get the error term, then the game will be very interesting. So the way we will analyze the error terms will be one of such problem will call as a autocorrelation problem. So that means autocorrelation is the correlation or it is the linear association among the error terms in this particular econometric setup. So now autocorrelations like multicollinearity, it is the degree of association, okay, degree of association among the error terms. In the multicollinearity we are discussing degree of association among the regressor, that too linear in nature. But in the case of autocorrelation, it may not be very specific linear issue, it may be non-linear in nature, okay. So that means it may be positive, it may be negative, it may be linear, it may be non-linear, like this, okay. So now once you have yt equal to alpha plus beta xt plus ut, then ut equal to rho ut minus 1 plus bt, okay. So rho generally lies between minus 1 to plus 1, okay. So you see here rho is the rho is the signal of autocorrelation problem, autocorrelation problem, okay, signal of autocorrelation problem. You see then there are 3 extremes. So rho equal to 0, rho equal to minus 1, rho equal to 1, rho greater than 1 and rho less than 1. Okay, so these are the five these are the three extremes, and besides there are two other cases. Okay, so if rho equal to 0, then it is an indication of no autocorrelation. So that means there is no degree of association between the two error terms. So that is called as a no autocorrelation situation, no autocorrelation problem. Okay, so this is rho, when rho equal to 0. Then this is called as a perfectly negatively autocorrelated. Okay, then it is perfectly positively autocorrelated. Okay, then so far as a greater than 1, less than 1, it is very complex issue how you have to properly interpret until unless you know the exact value of the term rho. Okay, so it greater than 1 means it may be 2, it may be 1.2, it may be 1.3, it may be 10, it may be 20, it may be 30, like this. So similarly less than 1 means it may be 0.1, 0.2, 0.3, 0.4, like this. So the range will be completely different. Until unless you know the exact range, then you cannot interpret properly, because like multicollinearity, autocorrelation cannot be removed completely. Okay, so autocorrelation most of the cases it will be always there, but so problem is how much you have to bear it. Okay, so what is the extent where the autocorrelation is not serious problem that will not affect the goodness fit of the model, because ultimately, so our aim is to have the best fitted models which is free from all such problems. So now to have the best fitted models, autocorrelation cannot be removed completely, but autocorrelation there should be specific range. If the value of autocorrelation will be that specific range, then obviously it will give you the indication of best fitness of the model. So otherwise it will be very problematic. So that means, like you see here, so, graphically the picture will be coming like this. So far as autocorrelation problem is concerned, let's say I will take it here ut and I will take it here ut minus 1. So there is this with respect to ut minus 1 I have to plot ut. So that means ut is a function of ut minus 1. So one way I have to take it ut minus 1. So corresponding to ut minus 1, the picture will be like this. So this may be another one way, this will be another way. Okay, so this is how the linear relationship all about. So far as the non-linear shape is concerned, then completely the picture will be like this. Okay, so this may be like this. So sometime up, sometime down, sometime positive, sometime negative. So like this, this is ut, this is ut minus 1. So that means here two things are very important. First thing is, what is the degree of association among the error terms? This is the first issue. If its degree is too high, it is a problem. If it is too low, it is a problem. So it should be the optimum one. So we will justify what should be the optimum one. So until unless you go to that particular structures, we cannot analyze it, we cannot say right now. Okay, so this is one aspect. And second aspect, the relationship, degree of association means it is otherwise known as a degree of relationship. Now the relationship can be linear, can be non-linear. Okay, can be positive, can be negative. So whether it is positive, negative, it is not at all issue. So ultimately, if it is a highly positive or highly negative, it is a low positive, low negative, then obviously it is a serious problem. So it should be in a range, and that range has to be perfectly optimum. So far as the best fitness of the model cannot be go other way around. Okay, so that is how the entire system all about. And the relationship can be non-linear also, which has one of the shortcomings in the case of multicollinearity. Multicollinearity is the purely linear relationship. Here there is no such linear relationship among the error terms. It can be linear, it can be non-linear. Okay, so ultimately what is this is the how the structure of the autocorrelation problem. So that means we get to know what is autocorrelation, how is its nature, and how we have to represent the situation. So that is what the autocorrelation. So now we like to know why autocorrelation usually happen in this or you can say occur in the case of econometric modeling. So the question is why there is a autocorrelation problem. So there is a term called as a sluggishness. Okay, most of the time series variable in the real life situation are very interdependent. Okay, if they are very interdependent, then obviously their committing of error will be also interdependent. Okay, so that's why there is a by default there will be autocorrelation problem. Okay, because it is the association among the error terms, but by real life situations what we have observed that most of the variables, time series variable are interdependent. If most the time series variable are interdependent, then their committing errors will be obviously by default will be interdependent. So that is one of the most important factor of why autocorrelation is exist in the econometric modeling. Second is the because of interpolation and extrapolation. Interpolation extrapolation is a mathematical technique which sometimes very helpful for increasing data points. Okay, increasing the size of the data points. So that means sometimes you will extrapolate data. For instance, suppose there are three variables, one variable has a 10, another variable is a 15, another variable is a 12. Okay, so that means it is going against the econometric systems, because econometric system needs that all these three variables have uniform observations, but now here 10, 15, 12. So obviously either you can go with 10 observations only without going for any interpolation and extrapolation, or you can say you have to extrapolate the data for 10 to 15 and 12 to 15, then you club it, or 10 to 12, then 15 out of 15 you have to take in 12, then already third variable 12 is there, so you can fit the model. That is another way. And third is you can extend both the variables to 15, then obviously it will be give you consistency sample size for all these three variables, so that you can go for estimations. This is one way how extrapolation will help you to increase the sample size. There is a very interesting techniques. It's not interpolation is one technique, but under this technique there are several methods through which you can extrapolate the data. Similarly, suppose there is some missing observation in between, so it will help with by this interpolation and extrapolation. You can also fulfill this missing observation. It may not be technically or mathematically it is correct, but theoretically or you can say practically it is not so problem. In fact, if you go statistically, then this process is also not very positive process until unless you check something else. Then one such thing is called as a autocorrelation. That means the moment you will use interpolation and extrapolation to increase the sample size, then obviously so it will lead to one hand it will increase the sample size and it will improve the degrees of freedom, and it will be very much helpful for significance of the parameters, or you can say overall fitness of the model. But in the other side it will add a extra problem to this issue is called as a autocorrelation. You remember one thing, if you have a model and all the specification parameters are as highly statistically significant, and R overall fitness of the model denoted by R square is absolutely very high, and F is also very significant, then it can be considered as a best fit models. But in the same times, if the autocorrelation value is extremely high or extremely low, then still the model cannot be considered as the best fitted model. So that means what we have discussed till now, the fitness of the model is not sufficient, because this is the necessary items which we have discussed. For today's lecture or in future lectures we will discuss several such type of issues where the best fitness of the model is not a very small problem or small issue. It is a very complicated, very complex pictures. You have to you will get to know when you have various aspects of knowledge on econometrics, then you can come to exactly means you come to exactly in a point that what is the it's not so easy that you will get the best fitted models after so many clicks only. So it is very, very complicated problem, because so many issues you have to discuss at a time. Okay, so that means interpolation and extrapolation is another cause which can bring the autocorrelation issue. Okay, so similarly So, this first is sluggishness, then second is interpolations or extrapolations, and third misspecification of random term. Okay. You see, generally we use error terms or random terms just to adjust the models. In a particular problem, in a particular setup, it is very difficult to identify all such variables which can influence y. There are certain factors which cannot be measured, which cannot be easily quantified, which cannot be easily represented in a or introduced in the particular systems, like drought, famine, earthquake, terrorist attack, log factors. These are the things it cannot be easily, you can say, measurable. So, for these factors the proxy is used as a error component. In fact, there is another type of proxy called as a dummy variable technique. So, we will discuss a little bit later, but in the case of for these variables or for these things we are introducing the error term. That means, we are observing that the variables which we are not incorporate, that can be influenced by u term only. But there are certain cases, it is not that every time whatever variable you could not identify, that you have to put it in error terms. So, there should not be a situation that the percentage of error should be means overtake the percentage of explained variable. So, if the explained percentage will be very high than error percentage, then obviously you are in the right track. But if the other way around, then you are in the wrong track, and that is one of the major issues, and that may be lead to the serious autocorrelation problem. Then we remember autocorrelation is a negative aspect of best fitness of the model. So, it has to be the value should be optimum, and it should be as per the accuracy of best fitness of the model. Otherwise, you have to redesign, reformulate, and re-estimate the model till you get the better fitted models. Okay. So, misspecification of random term or error term is also one of the factor which can influence. For instance, let us say last class I have discussed the stock price, that is BSE as a function of index of industrial productions, money supply, wholesale price index, and exchange rate. Okay. So, now this this particular by any chance means it is now as per my knowledge that the stock price as a function of economic growth, money supply, inflation, and exchange rate. So, artificially what I will do. So, I means obviously there is some when we will fit this model, there will be some error term here. So, the error term which can capture some of the other variables like government stability, or you can say governmental policy, or you can say market news, that may be influence the stock price. But since we are not representing all these items at a time here, and it cannot be fitted in the model directly. So, we are assuming that these you will capture all these weightage to this stock price. But you remember IIPG is measurable, quantified, and it is readily available. Money supply is quantified, measurable, readily available. Wholesale price index indicator of inflation is readily measurable, and it is also available. Exchange rate is also readily available. Okay. So, now by any chance artificially what we will do, we will drop inflation factors, or let us say we will influence you will drop the money supply factors. Then obviously, if you drop all these variable artificially, then it may be misspecified. Okay. It may be misspecified. It is not a question of maybe, it is definitely the case of misspecification. So, that is one way, the misspecification order, and similarly, and that leads to in fact a autocorrelation problem. Similarly, there is a mathematical imperfection of the model. For instance, we are discussing about this particular setup. In that particular setup, we are representing that the model will be linear in nature. Okay. So, the way we have discussed yi equal to alpha plus beta beta x, or you can say beta 1 x1, beta 2 x2, beta 3 x3 up to beta k xk. So, in that particular context, so we are putting all these things in a linear shape. Okay. But most of the things cannot be in a linear shape. So, there are certain things it can be non-linear in nature, but ultimately you have to transfer into linear by using lots of transformation rule, which we will discuss sometimes later. But if something needed transformation and if you are not doing and you are going with your original setup, then obviously it will lead to autocorrelation, okay, because by default the mathematical identification of the model is not correct. So there is a mathematical imperfection. So that is how the there is a way to, you can say, autocorrelation problem, okay. So this is misspecification of the random term or mathematical form of the models. There may be two regions, okay. Then I have just identified here that stock price as a function of index of industrial production, money supply, wholesale price index and exchange rate, okay. So I will add another item, say for CPI, consumer price index, okay. Sometimes wholesale price index and consumer price index, they may have different impact, but sometimes they look like same, okay. So now if I put BSE is a function of IIP, MS, wholesale price index and exchange rate, then obviously and also function of consumer price index, then obviously this is called as a over identify models, means unnecessarily you are introducing consumer price index where you have already used the inflation factor WPI. So now if you in that particular case, it will lead to one of such problem is called as, you can say, autocorrelation problem. Similarly, suppose this is the optimum case. We just increase this zoom so that it can be visible properly, right. Now you see here, so here we have taken BSE as a function of IIP, money supply, wholesale price index and exchange rate. So now if we add another variable, say consumer price index, into the systems, then there is enough possibility that the model is called as over identify models. If there is over identify models, then definitely there will be some kind of autocorrelation, means a high presence of autocorrelation. Similarly, what I will say, this may be the optimum case, but artificially I will drop this variable, say money supply, okay. So I will just now integrate BSE with IIP, WPI and ER. In that particular case, it is called as a under identify models, okay. Under identify model is also have a autocorrelation problem. That means you need to have a optimum model, okay. So optimum specification is very important. That is how very beginning I have very clearly mentioned that your theoretical knowledge must be very perfect, and before you go for econometric modeling, your problem formulation or setting up of the problem should be perfectly okay, okay. If it is not perfectly okay, then obviously there may be chance of misspecification of the random term, there may be chance of misspecification of the mathematical form of this model, there may be chance of, you can say, over identify models, then under identify model. In all these cases, it will be ultimate result is the high and high autocorrelation, and if this is the case, then obviously this model cannot be considered as a best fitted model, okay. So we must be very careful about that, okay. So that is how it's called as a over identify model or under identify model. So this is another reason, since sometimes there is in question of lag introductions, we are just discussing yt equal to alpha plus beta xt plus ut, but I will take a models like this. Or lag introduction means, instead of taking yt equal to alpha plus beta xt plus ut, I can take yt as a function of alpha plus beta yt minus 1 plus ut, or I can take yt equal to alpha plus beta 1 yt minus 1 plus beta 2 yt minus 2 plus ut. So this is how I can also extend. If I will follow this particular structure, then it is called as a lag introduction. If there is a lag introduction, then there is enough chance that multicollinearity will increase, and in the enough chance there is a high and high autocorrelation. So lag introduction will lead to autocorrelation problem, but you cannot avoid. These are all sometimes very much required for different point of view and for different objectives and different different interesting structure of econometric modeling. So these are all required. You cannot avoid all these things, but within that problem, so you have to find out the optimum solution. Okay, so this is how this. There is called as another cause is called as a manipulation of data. Sometimes lots of people with respect to lack of data availability, so they sometimes manipulate the data. The moment you will manipulate the data, then obviously one of the interesting problem will be the autocorrelation problem. So you must be very careful about for that. Okay, so another is manipulation of data. Then similarly, then there is called as a term testanarity. Okay, so testanarity is another issue through which you can say autocorrelation problem can be detected. If the variable is not testanary, that means what is mean by testanary? Testanary means a series having a mean variance are equal with respect to different time periods, then it will be called as a testanary. If there is any kind of volatility in between, then it is called as a non-testanary, or that is usually called as a unit root problem. We have a separate chapters to discuss all these unity root problems. So right now we are not discussing, but we remember one thing. So a non-testanary issue will be also autocorrelation problem. So similarly, then we have just now discussed the transformation rule. If the proper transformation rule is not okay, then obviously it will lead to autocorrelation problem. These are the these are the specification through which you can say we can say you have to represent the various regions so that autocorrelation can occur. So it is a by default there will be autocorrelation, because there are many factors which cannot be in your control, which can firstly lead to autocorrelation problem. Yes, we need to what is the alternative? We need to have some solution. Means you have to make lots of compromises to get a best fitted models. So now this is the cause behind this autocorrelation. Then next is the detection criteria. Detection criteria. Detection criteria. You remember one thing. There are numbers and numbers techniques. Techniques are available to measure the autocorrelation. The basic objective is to know what is the degree, that is more important, degree of association among the error terms. So what is the amount of degree of association, that is more important to project or to connect or to integrate the best fitness of the model. So one of the standard measure to you can say to know the level of level of autocorrelation is the called as a item called as a Durbin-Watson D statistic. It's otherwise called as a DW statistics. Okay, DW statistics. What is DW statistics? It is sometimes denoted as a small d. So d is calculated as a summation E2 minus 1 whole square, t equal to, of course it will be, this is E, okay, t equal to 2 to n by summation E t squares t equal to 1 to n. Why it is t equal to 2 here? Because if it is 1, then it becomes 0. So there is no such 0 term. So obviously if it is 2, then it will be t minus 1, then it will be 0. So obviously it's insignificant also, because of if you will start with t equal to 1. So obviously the starting point is equal to t minus t. So now you see, we like to know what is the Durbin-Watson D statistic D value, because D value will influence the degree of autocorrelation present in the systems. Okay, so how do we calculate for that? So we simplify this one. So this, if we simplify, then it will be coming summation Et squares plus summation Et minus 1 squares, okay, minus 2 summation Et into Et minus 1. Okay, so t equal to 2 to n, then this is summation t equal to 2 to n, then summation t equal to 1 to n divided by, of course t equal to 2 to n here. So summation Et squares, summation Et squares t equal to 1 to n. So this is how the simplification is all about. Okay, so now you see here, So what I have to do, but you remember summation E t square is equal to summation E t minus 1 square when t equal to 2 to infinity, t equal to 2 to infinity. When n stands to infinity, then you know the difference between E t and E t minus 1 will be equal. Okay, so in that case, that means when n and n is large and large and large, then obviously the log will be minimum, the log difference will be very minimum. So that's why summation E t square is equal to summation E t minus 1 squares. Okay, so that means, so we can call it 2 E t squares. So 2 summation E t squares, okay, t equal to 2 to n minus 2 summation E t minus 1 divided by okay, all right, summation E t squares t equal to 1 to n, t equal to 1 to n. Okay, so then this is t equal to 1 divided by summation E t squares t equal to 1 to n. Okay, so it's already there. So E t minus square equal to 1. So you will get the result 2 minus 2. This particular item is a raw component. You remember we start with yt equal to alpha plus beta xt plus ut, and ut equal to rho ut minus 1 plus bt. Okay, so that means rho means this rho is the covariance of ut minus 1 by ut. Okay, variance of ut. So this is how the rho component, and this is how the rho is all about. So that means, so we have the point here. So that means if we will simplify further, then d will be coming like this, d equal to 2 into 1 minus rho head. Okay, 1 minus rho head. So this is the Durbin-Watson d statistic. So d Durbin-Watson d statistic, d is represented by 2 into 1 minus rho. So you see here rho we have highlighted there, which is equal to minus 1 less than equal to 1. Okay, corresponding to this value, d value will also indicate the degree of association, because in the without having the Durbin-Watson statistic, theoretically we justify that if the rho value is diverse, means converse towards the minus 1, or you can say converse towards diverse towards minus 1, or you can say diverse towards plus 1, then obviously this will lead to autocorrelation problem at the higher degree. So if it is converse to 0, then obviously the degree of autocorrelation is very low. So now putting all these values, then we like to know what is the d structures. You see here, so we have the one case, different case is extreme case is rho equal to 0. If rho equal to 0, then d equal to 2 into 1 minus rho. Okay, 1 minus rho. So that means 2 into 1 minus 0. Okay, so it will be ultimately equal to 2. So that means when rho equal to 0, then that means if rho equal to 0, then d equal to simply 2. Okay, so now since rho equal to 0, no autocorrelation. So now when d value is there, then it will indicate that there is no autocorrelation. Okay, so similarly, if rho equal to minus 1, then obviously d equal to 2 into 1 minus into minus 1. So it will be equal to 2 into 1 plus 1, so 2. So this will be equal to 4 only. So that means when rho equal to minus 1, d equal to 4. So that means it is a perfectly negative correlations, perfectly negative autocorrelation. Okay, so now if we put rho equal to 1, then d equal to 2 into 1 minus 1. Okay, so d equal to 2 into 1 minus 1. So it is nothing but 0. So 2 into 0, it will equal to 0. Then it is called as a perfectly negative autocorrelations, perfectly negative autocorrelations. All right. So now what is the situation here? So the picture will be coming like this. So you see here, so I will draw here. So this is 0 fd, and I will draw a curve like this. So this is the situation where d equal to 2 and I will take d upper limit d Darwin upper limit Darwin Watson and Darwin lower limit, then this is 4 minus du, then this is 4 minus dl. Okay, so this side is negative auto and this side is positive auto and this side no auto, okay, no autocorrelations. Okay, so this is how this structure is all about. So that means you see here, if you simplify this one, so that means generally when we will go for any statistical software, particularly eViews, or you can say SPSS, or you can say MATLAB, etc., then obviously they will directly give you the Darwin-Watson value statistic. So now the way autocorrelation coefficient ranges between -1 to +1, then if you will simplify in terms of d, then d ranges from -1 is 2 here, so 4, then 0. Okay, so that means 0 less than 4, 4 less than 0 less than 4, 0 less than 4, 2. Okay, so 0 less than 4. So this will be d value. Okay, so this will be d value. When it is 0, 0 is called as a +1 situation. So that means this will become like this, and this will become to -1. It will be 4 like this. So in between, when there is a 2, then 2 will lead to, you can say, 0 autocorrelation. So that means, so there are, you can say, 3 extremes here so far as the Darwin-Watson statistic is concerned. So one extreme is 0, another extreme is 2, another extreme is say 4. Okay, so this is 0. So 0 means this is not this is 0 level. So that means it is a d equal to 0. So d equal to 2 and d equal to 4. Okay, so when d equal to 0, then obviously this particular structure is called as a when d equal to 0, it is coming positive, perfectly positive autocorrelation. Okay, d equal to 0, it will be coming negative autocorrelation. This is a negative autocorrelation. Okay, so this is no autocorrelations. Okay, this is positively negative. This is positively negatively autocorrelation. When d equal to 4. Okay, so this is positively negatively autocorrelation. Okay, so that means it is just in opposite direction. All right, this is in opposite direction. So there are means basic idea is here that the Darwin-Watson statistic has 3 different ranges. So d equal to 0, d equal to 2, d equal to 4. So that leads to the autocorrelation coefficient lies between -1 to +1. So now 0 to is one extreme range, and another extreme range is 2 to 4. Okay, so now if it is means it cannot go beyond 0 and it cannot go beyond, you can say, 4. That is suppose the d value statistic. So what is the conclusion here? Why we need transfer this autocorrelation coefficient to Darwin-Watson statistic? Because autocorrelation has the negative dimension and positive dimension, but here we are putting all these transformation into the positive dimension. Of course, the interpretation is a little bit different with a different value. So but we are in the positive side now. So now we have to see what is the positive sequence. That means if it is moving from 0 to 4, where the turning point is at the 2. So now if it is close to 2 this side, or close to this, close to the 2 that side, then obviously there is no such autocorrelation problem, or it is in a decreasing trend of autocorrelation towards the optimality. So now if it is close to 0, it is serious problem of autocorrelation. If it is close to 4, then it is serious problem of the autocorrelation. So ultimately the optimum range is in between something. So that means you have to find out its midpoint 0.2, and here you find out 2 to 4 the midpoint. Okay, so in between these two, if the autocorrelation is lies, then that is, you can say, consider as the best value or best association. In that association, in that range, then the model can be considered as the best. But if it is less than that or more than that, then obviously it will lead to serious problem. So in that case you have to redesign, re-estimate till you get the better fitted models. Okay, this is all means this is about the way of the Durbin-Watson statistic. However, this statistic has a one interesting limitation. One interesting limitation is that this particular statistic cannot be perfectly used when there is a distributive lag models, where there is a dependent variable and independent variable, and you can say lag dependent variable. So in that context, it is the term called as the Durbin H statistics. Durbin H statistic is generally defined as like this. So in that case, Durbin H statistic is calculated. Durbin H statistic, the value is rho head, which we have already derived, square root of t by 1 minus t variance of beta heads. Okay, and provided the model will be like this. So y equal to alpha plus beta yt minus 1 plus gamma xt plus ut. This is the model which we have derived, but ultimately this is the model which we derived, but ultimately our starting model is y equal to alpha plus beta xt. Okay, so you can put it here beta, you can put it here rho, no problem at all, just we are interchanging. So this is rho head equal to 1 minus d by 2, which we have derived here, because we have derived d equal to 2 into 2 minus 2 into 1 minus rho. So similarly, if we calculate simplify, then rho equal to 1 minus d by 2. Okay, so rho multiplied by t in minus 1 by t. T is number of sample observations, and variance of beta head will be like this. If you calculate it, then you will get Durbin H statistics. So then again Durbin H statistic will give you signal the presence of autocorrelation. In fact, the table is also there to know the optimum range. Okay, so this is how we have to detect, or you can say we have to know the degree of involvement of autocorrelation in the econometric modeling. All right. So now we get to know what is the Durbin-Watson statistic, and there are certain other tests also there's like Q test, then von Neumann ratio test, then BG test. So many things are there. For instance, if you take BG test, then your starting point will be like this: yt equal to alpha plus beta xt plus ut. Then what you have to do after estimation, then we will get alpha y head equal to alpha head plus beta head xt. Okay, so by the way we will get error term et, or you can say ut. So now what you have to do, so by any chance you will get alpha head, then beta head, standard error of alpha head, standard of beta head, t of alpha head, t of beta head, then r square, then f, then we will add another component now, Durbin-Watson strategy, particularly for this autocorrelation issue. Okay, so r square, f and d double, provided there must be ESS and RSS, then TSS. These are all the other side of the problem, in spite of the means in addition to this alpha head and beta head, t of alpha head and t of beta head. So you need to have, this is our assignment. So now if by any chance if Durbin-Watson statistic is close to 4, or you can say close to 0, then obviously you need to find out some solution, and then accordingly you have to test where is that exact process. Either you have to calculate this ones, or you have to be careful about this. That means this by any chance if there is such autocorrelation, then you have to this is how Durbin-Watson will give you indication. But another way, once you have ut and yt, then what you have to do, so you have to integrate with ut equal to alpha 0 plus alpha 1 xt plus gamma 1 yt minus 1 plus gamma 2 means rho 2 ut minus 2 plus continue like in. So you set another regression equation. Okay, then you have there r square value, here r square before the situation and r square after the situation. Okay, so that means you see let's say you don't like to use Durbin-Watson statistics. So what you have to do, usual procedure. So you have estimated models, y head equal to alpha head plus beta head x. Okay, provided a t of alpha head, t of beta head, then you get to know what is the significance of this particular parameter, whether it is 5% or 10% or 1%. Similarly for beta hat, then other statistic for overall fitness of the model is ESS, RSS, TSS, then R square, adjusted R square, and F statistic. Okay, but we are not discussing anything about Darwin-Watson statistic, but we sometimes suppose this specification are statistically significant this side and statistically significant of the other side, that is overall fitness of the model. Still the model cannot be considered as the best fitted model until unless you check this autocorrelation issue. So now we like to know whether this problem has autocorrelation or not. If autocorrelation, to what extent or to what degree. So Darwin-Watson is one of the statistics which already given the idea how we have to detect that autocorrelation problem and what is the optimum range where the existence of autocorrelation will not serious problem to best fitness of the model. So now here what you have to do, another way to detect the autocorrelation is the once you get ut, then you fit another regression equation ut as a function of xt, ut minus 1, ut minus 2, and you take the number of exact number of log length. So that is, there is a two statistic which we can detect that exact log length, that is called as AIC statistic, Akai information criteria, and similarly there is SBC criteria, FP prediction criteria. So like there is a lots of criteria like this. So it will choose the log length. On the basis of log length, then we have to fit a regression equation and have the R square value. So if then accordingly you have to find out a statistic n minus p into R square followed by chi-square distribution. Okay, so that means p is log order here, and n is the sample size. If this chi-square statistic is statistically significant, then there is a autocorrelation. Autocorrelation is a serious problem. If that particular item is not significant, then that means there may be autocorrelation, but it is not a serious problem. Ultimately, when the degree you go by this way, and if you are not interested for Darwin-Watson strategy, but by any chance if you will get R square, this chi-square is significant here, then obviously you have to redesign and reformulate. But when it will give you indication significant, then you are not sure what is the exactly range, whether by the criteria of Darwin-Watson statistic. If the Darwin-Watson value is close to 2, or you can say 1.9 or 2.2, something like this, then in that case it is not a problem. So autocorrelation is there, but that problem cannot be affect the goodness fit of the model. So this is not a serious issue. But in that case, it will detect the autocorrelation, but it will not give you the degree of involvement of autocorrelation. That's why Darwin-Watson statistic is considered as the best statistical tool to detect the autocorrelation problem. Okay, so this is how you get to know the structure of this autocorrelation problem, causes and its detection criteria. In fact, there are multiple criteria, but one of the interesting criteria is the Darwin-Watson statistic and its extreme range and optimum range. So now next question is what are the consequences if there is a high autocorrelation. Last class we have discussed that if there is a multicollinearity, again there is a problem whether you have to go ahead with the multicollinearity or you have to solve the multicollinearity. That means that depends upon objective specification. If your objective specification is go for prediction, then obviously high R square with low significant T ratio you can go ahead. But if it is vice versa, if for instance if for second objective for reliability is concerned, then obviously multicollinearity is a serious issue. So you have to remove first, then you have to go for forecasting or policy. Similarly in the autocorrelation. So autocorrelation, obviously when you will get a model, estimated models, it will go through this theorem, best linear unbiased estimator. That means what are the parameter you have received, that should be considered as a best. Okay, so now when there is autocorrelation, it will go against the blue property. Okay, so that means it cannot be best, it may not be linear, it may not be unbiased, that means it will give you high variance. If it is high variance, then obviously by default the statistical means this parameter will be low significant. Okay, so to get high significant, high weightage and high goodness fit of the model, then obviously the variance of that particular parameter should be less and less and less. So if but the by default, if there is autocorrelation problem, then obviously the variance will be very high for this and for a particular parameter. So that what you have to do ultimately. So you have to redesign or restructure the system till you get the best or optimum structure where you can use that model for, you can say, forecasting or policy use. So this is how the consequences side. So that means but most probably when you will go for when you have autocorrelation problem, so it will not affect all these blue property, it will affect only few properties. For instance, we have a properties called as unbiasedness. For instance, unbiasedness, then there is linearity, okay, then there is consistent, then there is efficiency. Okay, so that means when there is autocorrelation, these will be always there, but it will not affect much, but it will affect the efficiency property. That means what is efficiency? That means it is the cluster of minimum variance and unbiasedness. Unbiasedness property may be there, but it will lead to high and high variance. So that is how it can be means it can, in that case, that variable that model cannot be considered as a best method, and that cannot be also used for forecasting or policy use. So that means you need to have a solution. So that means if the particularly by Durbin-Watson criteria, if the value of autocorrelation is less than to say 1.5, or you can say more than to 2.5, then it is a serious problem. In that case, there is a redesign or re-estimation of that particular model. So now one of the such interesting, that means obvious problem is how to get out the solution. Okay, so what are the criteria to get the solution? So there are two standard techniques to solve this autocorrelation problem. So that is solutions issue. So solution is one standard of problem is use application of GLS technique, that is generalized least square methods. Okay, we are GLS technique, or sometimes if we apply WLS techniques, we will discuss detail when we will discuss the heteroscedasticity issue. So there is application of GLS technique, and another is you have to go for transformation. Okay, transformation of variable. Okay, so these are the two best solution to solve the autocorrelation problem. So that means if there is autocorrelation problem, instead of OLS you use different techniques like GLS and WLS. Even if you will apply other techniques like maximum likelihood estimator, that may be solve the problem, but the best technique is generalized least square to solve the autocorrelation problem. In addition to that, so you can go for transformation rule, so that the variable can be transferred into a proper shape. Then after transformation, if you use that particular variable for modeling, then obviously it will satisfy the minimum variance criteria. That means altogether the model will follow the blue theorem, best linear unbiased estimators. So in comparison with the previous situation and after transformation situation. So now but you if you will use transformation, immediately you should not use the transformation rules until unless there is some serious problem. So first you detect the problem, then you go for transformation. Otherwise, without any such problem, if you go for transformation, then you will lose the originality. Okay, so that's why you first detect the problem. If the problem is there, then you have to go for transformation and sort out the solution. This is how the autocorrelation all about. So we get to know what is the exact exact problem of autocorrelation, what is its impact, what are its feature, what is their natures, how it comes to the econometric modeling. That means what are the causes behind all the autocorrelation issue, then the detection criteria, and also its consequences, and finally what are the procedural measures through which we can solve the autocorrelation problem. With this we can conclude this particular session. Thank you very much. Have a nice day.